Good? All right.
Yep.
Hey, everybody. I'm Jared.
I'm Katya.
We built a Strainmeter for our project. This is what the Strainmeter looks like, this handsome guy. We made liberal use of zip ties, and we didn't intend on making a face out of him, but we used these zip ties to hold a phone for a time lapse, and this is our pulley and everything that goes into the Strainmeter. And it ended up just being a very personable young man. All right. Do you want to do the overview of what's strain?
Yeah, sure. So we are a strainmeter. So first we want to talk about strain. So the strain is basically the change of length over the original length. So what we are measuring is actually the change of length. So displacement.
Strainmeters come in all different kinds, different sensitivities. Some use an optical sensor or backscattered light from laser light, or maybe you've used a strain gauge or a borehole strain meter. There's all different kinds of strain meters you can use. Our particular instantiation of a strain meter often goes by the name of wireline extensometer. At least that's the name it's patented under. And essentially the idea of the operation here is you have a wire which is held under tension. It's anchored to the ground on one end, and then that line goes over to a free end that can move here. It's redirected over a pulley, and as these stations move with respect to each other, the extension or contraction of that line as it goes over the pulley is converted into a displacement signal. And so what you're measuring is displacement over the length of this wire. So that's the strain. But really we're measuring displacement. And you can make that displacement measurement in two ways. You can either, since this line is being redirected over a pulley, you can measure the rotation of that pulley, or you can directly measure the linear motion of the line. And we tried both.
Okay.
So this is how we were building our equipment. First, the idea was to build the pulley. We really struggled with this one, and with the help of the Leeman group, so we really made some things. And this is our pride, the pulley. So we manufactured this on this machine. So out of a steel rod. Eventually, it wasn't really a pulley; it was a shaft with two ends, where we drilled holes, where we installed our sensors, the rotary encoder and the rotary pod. We have this channel here where we fit the steel, the wire, yes, and two bearings that further will be encased in the angles, printed on 3D printer, so that we can ensure the free rotation of a shaft pulley. Then the second step, that's how we prepared our mass or weight. It's a steel rod, 1.75 inches in diameter and almost 20 inches long. So we had to cut it to reduce the mass, not to destroy our entire installation. And well, we installed this bullseye. Sorry, what's the name of it?
An eyeball.
Eyeball. Sorry for the English. And so that we can hang it on a wire.
And so just to add one thing, this is supposed to provide tension for the wire, because we need the wire to be able to move, but we need to make sure it doesn't wobble around too much, because that's going to be a displacement we don't want to measure.
That mass, then we encased in this PVC tube to prevent it from moving sideways. So here is where we install all our sensors. There are 3 of them. The rotary pod on this side, linear pod, you can see this greenish piece, so that it's actually part of the linear pod, and rotary encoder on this side. So this is lots of zip ties. So that's our installation inside the case, the lab jack, and the Raspberry Pi that was logging all the data.
Maybe we should mention the working principle behind each of the sensors. So the potentiometers are essentially, the potentiometer is a variable resistor, and so we use this as a voltage divider. These sensors will give you a voltage between 0 and 5 volts. You supply 5 volts and it gives you a range there. And so for the rotary potentiometer, as you spin it, the output is between 0 and 5 volts, and then it wraps around if you go more than one full turn. The linear potentiometer is like a slide whistle, and at 0, you get 0 volts, and as you extend it, you get 5 volts like that, or backwards. So those are both analog sensors. They're giving you a voltage, which we then digitize with the lab jack. The rotary encoder is a digital sensor, so it's supplying counts every time you apply a rotation to the encoder. There's a light inside, and it's counting flashes of light as you turn this thing. So it's an incremental optical rotary autoencoder.
So once we assembled everything, we had to do some troubleshooting, so not counting the zip ties. And so it turned out that our linear potentiometer, like the probe, was not touching the mat, so there was no way we could actually get any measurement. And again, so there was the idea how to solve it. We just used some acrylic plates to increase the height of the mass without actually increasing the mass. Yes.
Okay, and so what we need to do is get some scaling between the voltage that's output by the potentiometers and the counts that are output by the encoder, and convert those into the actual displacement that we're trying to measure. So to do this, we manually pulled the wire in 5 centimeter increments up to 25 centimeters and then back down to 0. And so you can see the range from 0 to 5 volts for the 2 potentiometers. The rotary encoder goes from 0 to around 40,000 counts. 40,000 counts. And so you can see the rotary encoder and the linear potentiometer have opposite signs, or the increments are in opposite directions. That's because they're mounted on opposite sides of the pulley. And I would say the rotary potentiometer is sort of by far the noisiest of our sensors, but I think they all reasonably well pick up relatively small displacements at the 5 centimeter level at least. And we have the calibrated values over on the side there. And because these are both 5 volts, 5 volt range sensors, and they both are spinning on the same pulley, one kind of interesting thing to note is that 0.23 volts per centimeter and 0.32 volts per centimeter, those should be the same. And so we have some discrepancy in how much the output is changing for the 2 rotary sensors. Probably sliding inside of the shaft because they're just friction fit. But perhaps we could glue them or something like that in the future. You want to talk about deployment?
Yeah. This is how our device looks like in the backyard of this building. It's fixed by a few rods. We try to use this nail, so but the soil is just too shallow to drill in the nail. And this is how we mount the other end of the wire. We pick a trench, an existing trench, a post to mount the wire to the ground, and we hope that the movement of the post is representation of movement of the ground. And here is a side view of what's going on at the post. And you can see there's a slope, and we're trying to make some ground movement, so we are actually cutting the top of the slope. But things, can you have a wild guess what's the failure mode of the slope once we cut the toe? So actually, we thought that the slope would fail like a landslide going this way, but actually the post is still it. And here's how we do the work. Can we visit YouTube?
Okay.
Here you go. Just take time.
The ground is unbelievably hard.
You can have few reference posts.
It's so much digging.
We can see some movement, but we see nothing.
I have blisters.
Yeah, so the soil is fantastic, right? As you can see, it exposed the entire post, and it's just standing there. This morning we tried very hard, and finally fell towards the station. It's very unexpected. And then we look at the toe of the post, we realize it's actually stuck into bouldery, shirty thing. So yeah, that's probably why the post is so stiff.
Okay. Our goal with this was to make a kind of analog to a landslide. Dig out, sort of undercut this slope and see it fail like that. And that's the sort of mindset we went into interpreting the data with. I think in reality, we were digging out and we were causing it to progressively lean, as Tim said. This is what our data actually looks like. So right off the bat, we have a 0 to 5 volt sensor. We're really working in a range of around half a volt. So these are very small rotations of the pulley. We're not getting huge travel of the suspended mass. The rotary potentiometer, although the calibration looked the noisiest, the actual data itself looks, I would say, the nicest. You can zoom in on these different displacements, and they line up across the different sensors. But when we actually did the deployment, the linear potentiometer doesn't seem to move at all. And we think the shaft of the potentiometer is getting, it's binding somehow, or
well, maybe because of the temperature, like when we tested it here, it's air conditioned and room and everything, so it was moving freely, but outside it's really hot, so maybe it expanded and this probe kind of got stuck there, so it wasn't moving enough.
It's also just a smaller displacement than we had in the calibration, and so maybe there's just more friction in the shaft than there is to actually rotate the pulley, and so it's not responding to the smaller displacements. But we could do another calibration at 1 centimeter, or we could look into that. But okay, so then we'll zoom in on some of these. Like I'll zoom in on this particular displacement event. That's what this looks like here. You can see it looks quite similar between the rotary encoder and the rotary potentiometer. You get this kind of initially higher strain rate, which then tapers off a bit and stabilizes. And then you can see we have a bunch of these other much smaller failure events. And so those happened not while we were digging. So these are just small relaxations of the ground, I guess. We were hoping for something more like this red curve, where this is displacement against time, where we would have some just some failures start, and then it would accelerate as the landslide started. But if you're willing to interpret this in that way at all, we definitely have something which is much more stable and less prone to runaway failure. This is what the data looks like when we left it overnight. Basically, nothing is moving, and we have this kind of low frequency oscillation. I don't think it could be temperature, it could be electronics. I'm not totally sure. But there was no really clear temperature effect. Like when it gets colder at night, the line didn't contract and pull it toward the station or anything like that. But we sampled it at 100 hertz.
100 hertz. Yeah.
So
why not? Okay, you can just click. This is the video of the collapse. So we kind of got desperate and we really wanted it to collapse. And we did some digging. Yeah, and yeah, we will see. Like after 30 seconds of that, like we will achieve what we intended for, but really not in the right direction. And well, my guess that maybe.
We talked for hours.
Well, it was actually like really little time. Yesterday we spent, I think, maybe 2 hours. It was really bad. So, and
Tim is just working.
we are much stronger now than we were before. That.
I'm trying to surcharge the so.
So, yeah, maybe the mass that we attached was just too heavy, and it that's why we saw it collapsed to the wrong side. Yes! There it is. Yep, so thank you.
Again? Okay, that's what we have. Thank you, guys. Yeah.
One of the first slides, I believe it was your calibration slide, where you had all three of your sensors. There was, on the linear potentiometer, there was like an odd spike at the very end of the time. I was wondering if there was maybe what that would be.
This at the end right there?
Yeah, on the linear potentiometer. I was wondering maybe was that it getting stuck, maybe? And then
Maybe I moved it.
Say that again?
Maybe I moved it manually, just like when we were moving the equipment, so I just checked how was the linear
movement
part.
here is just done by like pulling the wire.
Oh, so
by
there is a
hand.
movement.
And so we're standing pretty close to the tower with all of the instruments on it. I think it's really feasible that you could have just bumped the encoder.
It would only affect like just the one.
Yeah, they're not coupled in any way. It's just especially because it's the linear potentiometer. That's the only one that's not. It's not joined in any way to the rotary sensors. If both of the rotary sensors did something and the linear one didn't, that would also make sense. But at least these two should move together.
Okay.
Yeah.
I think what we learned from this is actually when we're using linear sensors like linear potentiometer or LVDT, we really want to make sure the system is really stiff, so you get linear movement. Otherwise, you're just stuck.
I was gonna say it looks to me like maybe the top one has a max and a min that it can't go past. So instead of going,
It's wrapping around for sure.
okay. So was the question about why it does that spike?
I think he was asking about this one.
Yeah.
Oh, I
right.
see.
Yeah.
I was just curious.
Yeah, so I mean, it didn't actually become an issue in our actual data, but if you wanted to measure larger displacements, you would have to like unwrap this rotary measurement.
Yeah, what did make sense because I thought they were all connected. So if you displace any part of this, you would measure a response across all three. But I do see what you're saying now.
Yeah, maybe we have one in the front. So this is a linear sensor. There's like a plunger that goes down like this, and it's just zip tied to the front down here. And then the other ones are plugged into the pulley.
So on a similar question, have that plot up. Why does the linear encoder have fewer steps than the rotary encoders?
Why does the linear
Encoder
The stair
has
steps on blue curve.
Steps.
There's a missing stair.
right here?
Well, no, on both sides.
Yeah, actually both sides.
That's a good question. I hadn't noticed that.
Yeah.
I guess it must have saturated. It's the only one that can bottom out, especially because it's not at 5 volts though. So, two possibilities.
Yeah,
One is that it binded or bound, or it stopped moving with the mass, which is something we saw in our field in our deployment. And the other option is that it just saturated again.
It is a problem.
Yeah, so
this should go back up to 5, I would think.
basically there is like the top of that metal tube, and here comes the probe of that linear potentiometer. But so that thing got stuck somehow. So maybe when we started like testing, calibrating, maybe the mass was just like moving up. So the rotary sensors, they were already getting measurements, and the linear only like reached it later.
But we're not really encouraging this thing to move freely. It's just tight on the edge here. Ideally, we would make a base plate, and you can mount this thing, it's actually horizontally. Next thing.
So what do you think?
Sorry. Otis had her hand up earlier. I'm sorry.
All right. How did you attach this to the landscape?
We put cinder blocks on this one. Let's see if we have.
Okay.
So we just plopped it there, and then this one was driven in with a lot of sweat.
So that was you stabilizing the actual instrument. How was the string gauge attached to the landscape? Or am I misunderstanding?
So
Oh, it's kind of
this is how so this side with the
Oh, okay.
the pole driven in, that's how we attach the wire. And then that
Yep.
goes over and it's tension with the mass that's hanging here. And then, the wire is what is then coupled to the string gauges. Emily, sorry.
What is the range of like the displacement you can measure, and like what is the scalability of it? Would you have to use like a smaller weight to measure smaller displacement at smaller distances, or?
That is a good question. We have about this much movement of the mass that we can
Okay.
measure.
It's like 25 centimeters. That I don't know in inches.
But if you wanted to get more than this,
Yeah.
if you wanted to get more than this,
Yeah.
you would need a way to keep tension in the line that doesn't rely on suspending a mass.
Okay.
So, I mean, you could imagine all different kinds of damping or
Yeah.
some kind of, you could spring load it maybe,
Yeah.
or,
Was that because of like the height that the weight could draw?
yeah,
Okay, so
before
like if
it
you have
hits
a bigger
the top and before it
Yeah,
hits the ground.
so smaller.
Yeah, if you wanted to,
Okay.
if you wanted a bigger tripod.
Would you bottom out your voltage, or can you adjust the voltage for the range?
You could get a sensor that operates over a larger
Okay.
voltage range, but
And what if you-
for the rotary sensors, that's not a problem because you can just unwrap it.
Okay.
For the linear sensor, you could do that as well.
How about if you wanted to measure like smaller displacement? Would that be possible with this setup?
How smaller? Like
let's
micro.
say 1 centimeter. Kind of
1
thing.
centimeter, but I think we can measure it with this. 1 centimeter is like within
Yeah, we
the
can
range.
measure 1 centimeter.
Yes.
I think we have a measurement here. We measured 0.63 centimeters in this
Yeah.
one. And there's other steps which are smaller than that, which are coherent across the different sensors.
Oh.
Like, I didn't make it super easy to see that, but you can like match up the different.
Okay.
For the most part.